Hi, my name is Braden, and I want to send your cat to Mars. But not using inefficient chemical rockets like this or this. I want to use efficient electric rockets like this to ensure that we can feed your cat for years to come. Unfortunately, testing big rockets is hard, whether chemical or electric. And testing electric rockets introduces some unique challenges because we have to test inside of big space simulation chambers like this. One of these problems is called backsputter, and here's how it works. Here's the inside of one of our test facilities. On the right, you see a thruster, and on the left, you see graphite plates that we use to armor the back wall. The thruster spits out a beam of high-speed ions. When they hit these plates, they're like tiny bullets, and they erode tiny flecks of the armor. These bits come back and coat the thruster. When enough of these bits stick to the thruster, we can see arcs, lightning, that force us to stop testing. So what do we do about this? Well, last year, I told you about my work building a force field generator to slow the ions down so that they don't have enough energy to knock bits off the armor. Unfortunately, we saw a new problem. The force field generator actually generated new ions and launched them back at the thruster with enough energy to knock bits of the thruster off. Not good. Here's an analogy. Imagine the USS Enterprise flies up to our force field generator. It fires its phaser into the generator, but instead of the force field absorbing the phaser, it creates lots and lots of tiny phasers and launches them all back out at the Enterprise. This is very bad. It could damage the Enterprise. Here's the good news, though. These beams don't come off in all directions. They come off like a fan, and the angle of that fan is called the divergence angle. Now, the electric field is perpendicular to the plate, so if we rotate the plate like this, or this, or this, we'd expect the fan to rotate as well. This implies that if we can learn theta, then we could build a beam catcher that looks something like this, so that when the Enterprise fires its phaser into the force field, the beams that come off fire away. We can deflect the ions away from the Enterprise. In this way, we can create a window of safety, and we can stick our thruster into this window of safety for safe testing. Yay! But how do we measure how well this works? To measure deposition, we use a tiny scale. Collecting carbon on the surface of this scale is like pouring salt on the surface. Ion erosion is like a strong wind that comes along and blows material off. Because we can measure both positive and negative changes in mass, we can measure the effect of carbon deposition and ion erosion. We put our upgraded beam catcher in a chamber downstream of a thruster. Next to the thruster, we mounted our very sensitive scale, along with a filter that would allow us to filter out the ions. Our first step was to find the divergence angle. To do this, we changed the angle of the beam catcher, and then we measured what the effect of the ion wind coming back was. Our second step was to change the strength of the force field. By making the field stronger, we would expect to see deposition reduce, and in this way we could prove that the beam catcher was actually doing what we wanted it to do. So how did we do? To find divergence angle, we changed the beam catcher angle and measured deposition with and without ions. Without ions, the background deposition is essentially constant. With ions, we see negative numbers indicating erosion. And in our experiments, erosion improved by 64 to 77% as we angled the beam catcher, which is great news. Now how about carbon reduction? To measure this, we fixed the angle of the beam catcher and varied the strength of the electric field, measuring only the carbon deposition with the ions filtered out. The data look like this. As you increase the electric field, carbon deposition clearly drops. Woohoo! However, as you continue to increase the field strength, deposition starts to rise. So what's happening here? Well, we put an ion filter in front of the scale, and this is the filter. It turns out that above 75 volts of field strength, the ions coming back have enough energy to break apart the filter. So what you're measuring there is filter, not carbon. Well, if that's the case, then what can we say about how well our beam catcher works? Well, we've seen in our data that angling the beam catcher does reduce ion erosion. We reduced it by 64 to 77% in these experiments, and that's great news for being able to use this force field. As for reducing carbon backsputter, we've seen that increasing the field strength up to 75 volts does reduce the backsputter. We reduced it by 45% in these experiments. Now, if it weren't for these pesky filter bits, we'd have expected this line to go all the way down to 0. And so future work will focus on building better filters or better sensors that don't need filters so that we can see that line go all the way to 0. I want to send your cat to Mars. Here at Michigan, we are already building the engines that we need to deliver Fluffy there. And this force field generator is enabling us to test these engines and ensure that Fluffy and you can live a long, happy life on Mars. Thanks for watching. Please like, share, and subscribe.